Okay, good afternoon, everyone. Welcome to Alan Turing Institute. This is our lecture series, and we have a couple of computer scientists for you today. Before we go into talking about them and their talks, which I won't do too much of, I've got some administrative stuff to say. Firstly, we're not expecting any fire alarm, so if we do hear a fire alarm, then obviously the exits are here, and you make your way out down the stairs and out into the quad in a calm and reasonable way. And I think it should be clear how to do that. The bathrooms are somewhere near here. I think somebody can point them out in the break, or if you have to rush out in the middle of this exciting talk, then I'm sure you can find them. So I'll give a couple of minutes about what the Alan Turing Institute is, and apologies to people who know that. But actually, even they'll probably be alarmed at what I say, because it may not be the same as what they think it is. But this is a joint venture between 5 universities funded by the Research Council of the UK government, and with partnership with a number of other organizations, Intel and Lloyd's Register and others, to do data science. And it's the National Institute for Data Science. There are many other institutes around that do data science. Many universities have their own local data science institute, but this is the big one at the moment in the UK. Probably in Europe, one of the biggest. And we're just kicking off. We're hiring researchers. We're just getting PhD students into a PhD program, which looks a little like a doctoral training program. And a lot of the emphasis is that, other than today's talks, is on mathematics and statistics and foundational ideas in that area. But we're going to hear more from the computer science side of things, of what you can do to build systems that may afford people a better world for doing data science in one way or another. So that's basically the gist of things. So we have a couple of 45-minute talks with 15 minutes scheduled for each talk for Q&A. We are live on the internet being videoed, and the video recordings will be put on the net. If you're worried about your privacy, then I am afraid that probably means you should avoid asking a question. When you ask a question, we'd like you to use a microphone, which we have people will pass around, so that people out on the net and on the recording will be able to hear the question. And we will also take questions from people who are attending this virtually on the net now. It'd be difficult to take questions from people watching a recording, I'm afraid. We haven't figured out how to do that yet. You can laugh at my jokes if you like. So that's basically pretty much all I want to say. There's a 15-minute coffee break between the two talks. There's a wine and cheese reception at the end of the second talk. And is there anything else I should add? No. Okay, so without further ado, let me very briefly introduce our first speaker. It's Professor Peter Hahn, who has a long, illustrious academic career working in separation logic and a number of other techniques relating to program verification, and then has made a partial transition from that world into using this stuff for real in an organization which many of us are quite familiar with, the world's current biggest online social network system, which is, like a lot of cloud-based services, has a very large code base. There's a lot of software out there. And so we're going to hear about his work in trying to make that better, a better world there, which is a pretty big challenge, as I think some of us are aware. So over to you then.
Right. Okay, so like John says, I'm working at Facebook now, and I used to be an academic, or I still am partly an academic, but we did a whole bunch of theory in academia and made a startup company. There's 2 of my collaborators, Calcagno and De Stefano, and our CEO, B. Lavender. We made a startup company, Minoitics. Minoitics joined Facebook in 2013, and so I found myself moving from academia, where I worked in theoretical computer science and program verification, and then I found myself in Facebook engineering. Before diving into things about program verification, I want to say a few things about what I found in Facebook engineering. On the first hand, Facebook is a company that's known for moving fast. So there are various posters adorning the walls of the company, like the foolish wait, and famously, move fast and break things. So sometimes I get up in the morning and I think, like, what am I actually doing? I mean, I worked in program verification, and let me give you a slogan for that subject. Move slowly and break almost nothing, right? So it might seem like what we're trying to do as academics is the worst possible fit in Facebook. But actually, what I found once I understood the engineering culture better and adapted what we were doing to that engineering culture, I found that the kind of work we were doing in program verification could work really well and actually could work better once we really understood this engineering context. So I want to say a bit more about that engineering context before diving into the program verification work that we're deploying. So the first thing is the scale. So let me talk about, not only is there big code, there's many, many millions of lines of code. Companies out there can have tens of millions of lines of code, hundreds of millions of lines of the code, sometimes billions of lines of code. Even more importantly than the size of the code is the pace at which it's changing. So let's talk about the momentum of the code. The momentum of the code in industry, especially industries close to the internet, is absolutely huge. So there are more than 1 million source control commands per day, trying to check things in, for instance, to the source code. There are more than 100,000 commits per week. The commits are the check-ins. So things are moving very, very fast. So you shouldn't think of code as a fixed artifact. I think of it as an evolving system, except that it's evolving concurrently. Many people are changing it, crashing changes into the code base at the same time, and it's evolving very rapidly. So in this rapidly moving system, we're going to end up deploying program verification technology, which would have been thought of originally in a completely different engineering mindset. Like the mindset of program verification, for the most part, followed what you would call the water flow model, where you start with a design and then eventually you get code. What's practiced in Facebook and other companies, the code is changing all the time. It's more of an iterative model. I'm going to show you how that works. But besides what I talk about program verification, keeping this code in shape is very important for Facebook, for our code, and for companies that are similar to that. Keeping that code in shape is very important. And because the momentum is so huge, it causes great challenges that we've never seen before. So even the most basic things like source control means, how do I check code into my code base? Well, there are a whole bunch of programmers checking code into the code base concurrently, thousands of programmers. And it turns out that this is such a challenge and an important problem that even this thing that you might have thought would have been very basic, how do I check code into the code base? We employ people to make that faster. So for instance, there's a source control system called Mercurial, which deals with check-ins to the code base. What we've got is we've got a team that works on Mercurial, and when we've got a big code base and somebody needs to put a new piece of code in, what you would rather not have the source control system do is have to run through the whole code base to make a check whether that's consistent. You would like to make simple local checks. And so we have people, this is talking about sparse checkouts. A sparse checkout, you're checking out only little bits of the code base that you need. A trend that I'm going to talk about when we're talking about the momentum of code changes is it's not enough to have algorithms that are very fast running over a complete data structure or a complete system. They have to work well incrementally over little bits of the system in order to keep pace with the code changes of the programmers. So we have a team that's working on Mercurial. And we've made loads of speed ups to Mercurial, and Mercurial is in some cases faster than a competitor system that many people use called Git. And why would a company like Facebook be contributing to something like Mercurial for code check-in system, source control system? The reason is very simple. Moving fast, the whole point of moving fast is to allow the company to innovate quickly. Every time we make a software engineer wait, that's making us innovate more slowly. So let me put it like this. Suppose I try to do a command which checks something into the code repository, and I have to wait, because the code repository is big, I have to wait 100 seconds. Well, 100 seconds is long enough. The person might get bored and they might, go start checking email or something like that. They might context switch. And so then they come back who knows how much later. And so they've lost the flow, right? Whereas if you can do it in 5 seconds, then they can just continue on. And so we've actually made changes to Mercurial, which in some cases will take you from the hundreds of seconds down to the 5 seconds. And when you then pile this up over thousands of programmers, it makes sense for an organization like Facebook to contribute to an open source thing like Mercurial to speed it up, because that speeds up our programmers that much and lets us be more productive. So not only Facebook, Google, you'll find many of the big companies work on things like this, because what we take off the shelf has never seen the problems at the scale that Facebook, Google, Twitter, and the like are dealing with. We've never dealt with those problems before, and so the standard tools are not up for quickly working with those code bases. Okay, so the general reason is the move fast, the ideal to move fast translates into having a software engineering culture and also an infrastructure which we want the humans to, we want the computers doing the work. We don't want the humans waiting for the computer to finish. So, okay, let me move on now, talk about a few more things. So still not program verification yet, just some of the context. So in keeping the code in shape, there's a number of things that you have to do. The first thing you have to do is you have to build the code. You have to be able to produce the runnable artifacts. Then there's dynamic, which is testing. There is testing. And then there's static analysis, which I'm going to talk about, infer. And a lot of this happens inside of what's called the continuous integration infrastructure, the CI infrastructure. And we've got our own one of those, Sandcastle as well. So let me talk for a second about the build system, Buck. So when I landed at Facebook, this really, really struck me. So I landed and I found there was a team making the build system. And the build system calls a compiler, takes a code base, calls the compiler in the right way to produce the runnable artifacts. And I was just stunned that the company doesn't, there's not something out there that they just use. They are working on their own. And then I found out, well, guess what? Google has their own too, Blaze. Guess what? Twitter has their own too, Pants. So all of the major companies are encountering problems just in building software that are difficult enough where they need to make their own teams to do this. And I was struck by it because this seems like the most basic thing possible to build the software. But what's actually happening is the scale at which we're seeing code now and the pace at which it's changing has not been seen before. And so we're having to revisit very, very basic problems as a result. So we've got our own team, Buck, which makes a build system. And Buck is good. So for instance, to build Instagram with the previous build system we were using would take 2 minutes, would be to build the Instagram Android app. Then after Buck, it would take 15 seconds. So the huge difference this makes, again, is that the human wants to build, I've made the change to the app, now I want to build it, I wait 15 seconds, I can tolerate that and then start working with it. 2 minutes, I'm gone, I'm going to do something else. It makes a huge difference. Also, this is going to run in the data center to keep the code clean, and so that time will build up in the data center as well and cost us money. So performance, you might think that we've got these very fast computers these days, right? We've got very fast computers and we're not so worried about perf anymore. Moving from academia into the industry, performance is crucial. It's crucial at all times. We're always trying for more speed ups. Now, so I'm not going to talk about the dynamic, the testing there. So we do lots of testing inside Facebook. I am going to talk about static analysis. But before I talk about the static analysis, let me talk about what's happening in this thing, the continuous integration system, by taking you through the life cycle, how code gets from the programmer's desktop to the phone in this instance. So it takes 1 to 2 weeks, and it goes through a bunch of steps. So first, the programmer is writing the code, testing locally on their own machine. Then they make what we call a diff. It's a code mod, a code modification. Code modification is then shipped into the data center. Sandcastle is something running in the data center. What this thing Sandcastle does, so at this point, humans are looking at the code as well, code reviewers, but in the data center, loads of things are fired up to try to make sure the code's okay. First thing, can it build? Second thing, does it pass various tests? Lots of tests are run automatically. Lots of other things, static analysis is like testing, that's also run automatically. After this, we get to the land phase. Land is when you, in a sense, check in. You check in the code. So the code only gets checked in after it's gone through lots of checking in the data center. Then there's land castle. At this point, longer running tests can also occur. At this point, we might want to get feedback back to the developers quickly, so we need to run quick running tests and quick running static analysis. Here, there might be time for longer running things. So eventually, we're happy and we land the code. And then we don't quite give it to the phones at that moment. Before sending it to the phones, there's something called branch cut. And there's what's called a release candidate. So what happens is there's a release candidate and the employees of Facebook, like I will have Messenger or Instagram on my phone, which is the person, not the one that you have, the one before the one that you have. And we have thousands of employees by using that, testing it out. And so the release candidate is there. And so the continuous means there are other long-running tests, including performance tests, which at this moment is up to a week. There's up to a week this phase before we get to production. And then if any really bad problems are found, we make changes and what's called, we pull in changes here. What's called cherry picking a diff. So it would be like a diff here, but we pull changes into the release candidate and eventually we get to production. So you see lots is going on before we get to prod. So now what I would like to do, so having given you the general framework for how code is kept in shape is this kind of thing, where tests, static analysis, and whatnot are run in the data center, and then there's further testing in the data center and by employees later. So all this work is done to keep the code in shape before we get it to production. So now I'm going to zoom in on the specific work that we do in the static analysis. This is the part that I know the best, that we work on. And this is going to be my only sort of technical computer science slide. Because so what we've got is we've got millions of lines of code. Somebody submits a code change. We need to get feedback to developers reasonably quickly, ideally in 10 minutes, maybe within 30 minutes might be okay. So we've got millions of lines of code. We need to deal with that quickly. Program verification is an undecidable problem, never mind a quadratic problem or something like that, right? So it would be bad to have to analyze the entire code base with the program analysis algorithm. So luckily, before we came to Facebook, we devised an algorithm to do things in what's called a compositional way or a local way. And I'm going to illustrate it right here. So what we do is we get a procedure. And what we do is we start what's called symbolic execution of the procedure. So we start from emp, which means I know nothing, up at the top. Then, after I do a malloc, let's forget about the fact that malloc might fail. After I do one malloc, I get that x points to nil, plus I do a pointer swing there. After I do a second malloc, I get x points to nil and separately z points to nil. Then I'm going to call this procedure foo. I don't know the code for foo, but I know that it's got a specification. The specification says if I have two separate linked lists in memory, and I call foo as the precondition, then as the postcondition I have one linked list in memory. Now this might be an algorithm to merge two linked lists, say, but we don't know that. We don't know the code. All we know is the spec. The spec might have been given by a human, or actually it might have been discovered previously by a program analysis algorithm. But in either case, at this point, what we do is we call a very funky gadget called a bi-abductive theorem prover. So what we do is we try to make sure that the precondition at the call site, x points to nil and separately z points to nil, matches up with list x and separately list y. And it doesn't quite match up, but it almost matches up. What we need to do is we need to say, if only, so we've got that x points to nil and separately z points to nil, but we don't know that y. We don't know that we've got a linked list y. We need to have a linked list y to satisfy the precondition. So on the left here, we fill this in, if only we had something that could satisfy that precondition. That's called the anti-frame, and this problem in logic is called abduction. inference of something to the left of the turnstile. If only. The z points to nil is what's called the frame, which is a problem from artificial intelligence called the frame problem, which talks about that which doesn't change. And so we need to, so my colleagues, like I think Calcagno, I would say, figured out the way algorithmically to discover these, the frames, and my colleague De Stefano figured out how to algorithmically discover these, the abductees, I'll call them, the anti-frames. So we discover the anti-frame list Y, and then what we do is, we throw it up to the precondition. You see that? We change the precondition. We say, if only we had list Y, then we could symbolically execute this procedure. We throw z points to nil in the postcondition. The next call is an easier one. And in the end, we get a list Y as the precondition and list return as the postcondition. So what's really amazing here is starting from the bare code and the specification of the inner procedure, I've discovered a pre and a post. Usually in program verification, you have to give the pre and the post, or at least the pre. I've discovered them. So this amazingly simple but amazing thing opens the door to scalable program analysis. So I can analyze my procedures in isolation. Some of them, I can tie the specifications together. Sometimes I can't. It might be a bug, or it might be that my program verifier, my algorithm is too stupid. I mean, it's not clever enough. Nobody's ever made an algorithm clever enough to say verify the entirety of a big program like Linux or the Facebook apps. But we can get parts of it. And the interesting thing here is that this algorithm that I've just said is, suppose each procedure I had a bound on how the running time of my algorithm for each procedure. Because it treats them all independently, the procedures independently, I'm going to have a linear algorithm, right? And so dealing with big code, it's very, very good to have algorithms, which at least when we arrange our parameters correctly for the complexity formula, it's very, very good to have linear things. It's very, very bad to have quadratic things dealing with big code. And so we've got that. Now, so we had a program analysis algorithm which could run on big code. So we could then generate lists of bugs and give them to the programmers. And that's what we did. And we were very excited about being able to do this. We thought, oh my God, we've got an algorithm that can run on big code. And I worked really hard to lower what's called the false positive rate, the bad bug reports coming from the analysis. I worked really hard to do that because as an academic, I was taught this is the most important thing about static analysis, is having a low false positive rate. So we did that, and we deployed it, and guess what? The programmers at Facebook didn't congratulate us. They didn't come running and saying, we were so awesome and we're going to fix all. Actually, it was very hard to get them to fix the bugs. And that's because I didn't understand their model of working. So this doesn't fit the move fast. So in the move fast, they're working, and maybe if I could tell them at that moment, it would be good. But I do something overnight. Meanwhile, they've changed a lot more. They get an email from me in the morning saying, hey, would you please fix this? Maybe they've changed their code. Maybe I've emailed the wrong person. So the biggest problem here is that this slow model, which is more like batch mode model, has it doesn't fit with the way the programmers are working. So a better deployment model fitted this diff idea that I showed you before. So in the diff idea, we know that programmers submit changes to the code base, right? And when they submit changes to the code base, other programmers look at those changes in the code review system and talk to them about it. Now, what the program analysis algorithm, to fit better with the working model of the programmers, instead of analyzing the whole code base and giving me a list of bugs, it's better to analyze just the code change, what they're thinking about, and tell me about what's happening with that code change. And now, the algorithm that I showed you before, which analyzes things one procedure at a time, you see it fits perfectly with that, right? I don't need to go analyze the whole code base, actually. I just have to analyze the procedures that have changed. And so this solves one really bad problem with the slower deployment model I said before, called the relevance problem. So the relevance problem is I need to give people feedback that's relevant to them in tune when they're thinking about it, actually. And this kind of deployment model solves that much better than the previous deployment model. So this is the way it works. So a developer makes a code change called a diff. In the CI system, continuous integration system, the data center, Infer gets fired up. Code reviewers, by the way, are talking about the diff at the same time. Maybe Infer finds a bug. And so Infer is just like a robot that's participating in the code review along with the other humans that are participating in the code review. And what it does is there's some code, right? And this is an example of an Infer report. It says there might be a null dereference object last assigned on line 12 could be null dereferenced at line 13. So it makes comments on the code like this for people to read as they're deciding whether to accept the code or whether to change the code. And so eventually, maybe the code reviewers are happy and Infer is happy, and then the code gets shipped to the product. Okay, so now about this moving fast, the importance of it, I can't overstate it. So here was a case where one of the developers, Infer was slow for a while. We had some performance regressions. Then we made it run faster, and the developer reached out to us and said, "Oh, it's so amazingly fast right now. It's a way better experience. Previously, it caused me to lose context." And so the developer's congratulating us on giving him or her feedback more quickly. A more entertaining thing is breaking things. So there's this slogan, move fast and break things, which is usually misunderstood. So when I worked in program verification as an academic, I didn't want to make any mistakes, right? So first of all, I wanted my algorithms to be what's called sound, and I still do. And second of all, I would be very careful to give something to people that was less than perfect. I would be very careful about that. Now, we give things early to the programmers in order to get feedback from them for when we make mistakes. And this has let us iterate more quickly and make a better tool. And the reason we do that is because breaking things at Facebook, really, a large part of it means if we try something out and we make a mistake, a little mistake usually, then we will be forgiven for it. So try things is what it's saying. And so in this instance, Infer had a false positive error report. And I was a bit worried. I said, that's pretty subtle. Thanks for pointing that out, I said to the developer. And I thought, oh no, we've made a false positive report. But instead, the developer gets back to me and says, oh, it's a false positive, but thanks for following up. I found it to be useful and it saved me lots of trouble other times. So as a result of multiple interactions like this, we are less scared about making mistakes in that we will ship features to the programmers earlier than we would have otherwise done. And this has allowed us to evolve the tool over time and make a better tool than we would have otherwise done. Thanks for the tool. So it's such a positive attitude we're getting from the programmers. It's quite amazing. My biggest fear was committing the sin of false positives, and instead I end up with the developer thanking us for the tool. Okay, so I'd like to go through just a couple of little programming examples. So this is Objective-C code. So Objective-C is the code that we use to run the apps on the iPhone, right? So Objective-C, I don't know how many computer scientists we have in the room, but Brad, don't you answer this question. Objective-C uses something called automatic reference counting to reclaim memory. It doesn't use the more normal kind of garbage collection. Who knows about a problem with automatic reference counting? Come on, somebody must know. Martin Berger, yes? What's the problem? Cycles. So when there are cycles in the unreachable state in the garbage, then it won't be collected by a normal automatic reference count. And in fact, there's a fellow at Facebook, Matt Galloway, who wrote a book on Objective-C. And he sits next to us. And DiStefano on our team talks to him, but what's your biggest problem? Biggest problem is this. These are hard to track down. And so they come in a particularly tricky form, where here, the up arrow is in what in functional programming on line 20 is a lambda. So Objective-C has lambdas. And so little c is allocated on line 19. On line 20, there's this lambda expression with c.name inside of it. Well, that generates a closure at runtime, which is an object. It generates an object. So there are two objects, c and this lambda expression, which reference one another, a cycle. Then they get out of scope. So we've got what's called garbage, which is a cycle. And so this is not going to be collected by the Objective-C runtime. So this is an example of the bad kind of bug. So after talking to Galloway, DeStefano made a check for this. So this would be an advanced kind of check in automatic program analysis. Very few program analyses that are deployed in the real world would handle this sort of thing because it means you have to understand a little bit of lambda and you have to understand cyclic data structures in memory, at least, to get this. Both of these things are very advanced program analysis. This is an easy example, but very advanced. Okay, next one is from OpenSSL. So OpenSSL famously had the Heartbleed disaster, right? You remember the Heartbleed bug. And the Infer program analyzer did not find the Heartbleed bug in common with every other program analyzer, which was embarrassing for the field, but be that as it may. After the Heartbleed disaster happened, I ran Infer on OpenSSL to see what it would find, and it did find 15 other bugs, which then we submitted to OpenSSL and got them fixed. And so this is one of them. So here, you call this thing called OpenSSL malloc, and then you dereference it immediately, the P, and it looks quite easy, an easy bug, except that malloc normally can return null, as C programmers are used to. Now, the problem though is that this OpenSSL malloc isn't malloc, it's a wrapper for a much more complicated program. And so what Infer has had to do is it's had to go off and discover a pre-post spec for this OpenSSL malloc is itself defined in terms of something called cryptomalloc. It discovered the pre and post spec, like I showed you on the earlier slide, and then it used that in trying to analyze this, then it found the error. So you see, this ability to go off and find the pre-post spec was a crucial thing to be able to do to be able to find this sort of, looks easy, but actually is not so easy kind of bug. Here's another one. Another one in OpenSSL, which is, there's this function here, GM time, x509 GM time, which might return null. And then there's an immediate null dereference. Now, Infer finds this, and it was fixed by the developers. But there's something quite interesting. So this GM time function is a fairly complicated thing. And there are some nulls eventually that might get returned. But what Infer has not done is this. It's not proven that this null will actually definitely happen or could happen at runtime. We don't know. Infer doesn't know that. We've generated a bug trace, but it didn't go all the way back to the beginning of the program. But the developer fixed it. And this is an interesting thing. In program verification, people often talk about true bugs and false positives. And the actual situation is that that's a nice concept, but in practice, there's this in-between I don't know area. And you're almost always in the in-between I don't know area. And so Infer is in the in-between I don't know area here, but so are the humans. And just to drive that home even more, we've run Infer on there's a code review system by Google called Garrett. And we ran Infer on it, and we found a security issue. The security issue has the host name of the SSL socket was not verified. It's a security issue. And we reported it to the Google team, and they fixed the bug. This is the way Infer says it. Infer talks about the bug. But the more interesting point is that my colleagues, Sam Blackshear and Jules Villard, who worked on this, we had two colleagues who are experts, absolute experts in program analysis. They studied this for hours, and they didn't know if it was a real bug or not. Then we got in touch with a security expert inside Facebook, and he said, it seems like it could be legitimate, but he doesn't know for sure if it's a bug. Then we got in touch with the Googlers. I think their attitude, I don't know exactly what they said, but their attitude was something like, it seems legitimate and we'll fix it. But their attitude wasn't like, we definitely know that this will happen. So this is, again, hours were spent by total experts not knowing if it's a true bug or not, but thinking that it's something that should be fixed. So the reason I'm hammering on about this is because one thing I've really learned moving into the industry is that I was taught as an academic that the concept of false positive rate, or rate at which you find true bugs versus false bugs, is the most important thing in program analysis. Now that I work in industry, I think that that's hugely overrated, that idea. Because practically, the humans don't know what are the true bugs and the false positive necessarily. And secondly, as the code bases are changing very, very fast, these things are not measurable. Because we don't know, we can't measure them. If you've got a measure, you should be able to measure it, right? And this rate, the false positive rate, is practically unmeasurable. On the other hand, we work with something that is measurable called the fix rate. The rate at which we report bugs to the developers, what's the rate at which they address the issue? As you see, that is measurable, and that speaks to the value brought to the programmers as opposed to this other more abstract thing called the false positive rate. So we've moved to using fix rate as a proxy for analysis quality instead of false positive rate. So the status of what we do is that each month, Infer, what I've been talking about, runs on the modifications to the mobile apps, the Facebook mobile apps. So Facebook, Messenger, Instagram, and WhatsApp, it runs on those. Each month, hundreds of those potential bugs are reported by Infer and fixed by the developers before they reach the phones. The fix rate, I know nothing about the false positive rate, or I don't know exactly what it is, but the fix rate as we measure it is between 70 to 80% of the bugs, the potential bugs that we report. 70 to 80% each month are fixed by the developers. And in the process, there's this funky theorem prover going on in the background, which is allowing us to do this. So that's the status inside. Then we've open sourced the tool last year. So see, that's really nice too. Facebook and Silicon Valley actually have the idea that software engineering is difficult. We don't have all of the answers about software engineering. There's lots of sharing of ideas between the companies on how to do software engineering. And at Facebook anyhow, we're shipping our internal tools to the external world. And so this has a lot of benefits for us. By getting feedback from the people in the world, we can make our tools better and make our products better, right? So the tools get better as a result of doing this. So we don't just try to guard our secrets. We give away lots of the key tech. So anyhow, so we've open sourced. And open sourcing was fun. That got some attention. So one person, so little individuals start fixing bugs. So the world's software gets better, not just one company's software gets better as a result of doing this. Another person, after playing around with Infer, said that he thought it was badass. And so, I mean, who are we to disagree with this person? Another person fixed a bunch of bugs flagged by Infer. See, that's just wonderful, right? That's just wonderful working for one of these big tech companies, but affecting lots of the world's software, giving back. So there's an article in Wired and TechCrunch and things like that. So that was quite fun. And then let me see if I'm sure people in this room don't know. Who knows what Hacker News is? Oh, I love that. That's more than usual for the academic audience, and I'm glad that you know this. So Hacker News is where hackers or programmers go to get their news. It's something run by an org called Y Combinator. Now, so there was a thread about Infer on Hacker News when it came out, and there was one very entertaining comment. Legend has it that there's a small room at Facebook headquarters containing a quorum of all camel committers, all of them French for some reason, and hacking away at a level of abstraction beyond the ken of mortal man. You see, Infer is written in OCaml, which is like a really excellent functional programming language. And one of the people on our team, Jules Villard, happens to be French. And so his answer on that thread was, I'm posting from that very room right now. So that was nice. So that was a lot of fun. Okay, so we've developed for inside Facebook. We've shipped it to the outside world so many individuals can use it. Now, several other companies have picked it up and are using it internally as well in a similar way. So Spotify, Uber, and Q1. Q1 is a company that does software as a service. So these three companies have confirmed that they're using it, and there are other companies that are using it that we're hoping to get confirmations on, and lots of individuals. So that's a lot of fun. Now, just to end, I just want to, I've banged on about the same point again and again, but sometimes people don't really get the point, so I'm going to drive it home one last time. So I gave this blurb to one of my friends, Dan Geeka, a few weeks ago. Dan Geeka is a researcher in programming languages at Birmingham University. And after I gave that blurb, Dan said to me, this is a conversation on Facebook Messenger, "Hey Peter, sorry to bug you, but I have a nagging question. Why does infer need to run live as part of the build process?" So running on the diffs, like I showed you. "Why can't it run in batch mode to find more?" See, this is what the computer scientist always wants to do, go deeper, find more. And I said, it doesn't need to run live. It's just much better to do so. Batch mode equals much less impact. Batch mode equals, like I'm just speaking to my friend here, like very bluntly, batch, too late, out of the developer's workflow, much harder to get the bugs fixed. Batch mode is too late. And then Moshe Vardi has been going around, he's got a good principle that he's been saying. He states it like this: the brainiac often loses to the speed demon. And Cristiano Calcagno states it slightly differently. His take on Vardi's principle is, it's better to be dumb and fast than smart and slow. And so then I continued on with Dan. Batch mode, the fix rate near 0%. And Dan says, this is quite amazing. And then live mode, the fix rate was approximately 80% at that point. And that's for technically the same analysis. This is the impact of moving fast. And so for the same analysis that has the same false positive rate, this deployment model had the fix rate approximating 80%. The batch mode had the fix rate very low. So Dan says, wow. So what I want to say, really in conclusion, is that so we've got big code bases. More importantly, they're changing fast. This is happening more and more. The world's code isn't going to get any smaller. The world's code is going to get bigger. People are going to be changing it faster. And so I think, especially in testing and program verification and analysis, but more generally, what I think we need to do more in computer science research is to embrace this fact that the code's going to be changing fast and it's going to be big. And so I think that the computer scientists need to listen to Vardi's principle actually here and consult your inner speed demon. Don't just go for deeper and slower. Okay? Thank you.
Okay, so we have, having kept time, we have 15 minutes for questions before the coffee break. So first of all, can we take any questions from the floor in the room? Okay, you were first. Do we have a microphone? Yeah, can... thanks. So we do a crowdsourcing delivery of microphones. Thanks.
Thank you very much. I'm Tahir from the Oxford University. I noticed in one of the headlines, info was called Facebook AI. Is it just a catchy title, or there is a kind of artificial intelligence happening?
I didn't call that. A reporter asked me a question which I answered correctly. So, so there's nothing that wrong with it. So we don't call it AI, but has it got techniques motivated by artificial intelligence within it? Yes. The frame problem comes from artificial intelligence in the 1960s, and that's hugely influenced what's going on. But now this is like logical AI or symbolic AI was before sort of the more numeric AI. And so, yeah, so I wouldn't say it's an AI tool, but it does some reasoning that's hugely influenced by ideas from the AI literature.
Question up at the front here. state your name and institution.
Brad Carr from UCL. Hi, Peter. I enjoyed your talk a lot. One thing I found fascinating about your talk and your experience is that the emphasis on not worrying about false positives seems almost diametrically opposed to, say, things you hear Coverity say about, really needing to cut down on the false positives for their tool to be a commercial success. Yeah. And so I guess my question is it possible that you're both right at the same time? Is there something about your deployment environment and the culture of Facebook, or even maybe your being in-house with the developers you're serving, that lets you sort of improve uptake and improving the fix rate by interacting with them more in-house? Or do you really think that Coverity should be going this way too?
I think they probably are, except that they don't state it in the same terms as me. Because I don't say that false positive rate is irrelevant. I just say it's hugely overrated, and you can't measure it, is what I say. So, in fact, if we had if we actually had a horrendous false positive rate, then we wouldn't get the good fix rate. Yeah, so that's true. But even Andy Chow, the Coverity CEO, gave a talk at Pupple 2016, I believe it was, where he said that their biggest problem is loads of bugs sitting inside companies that aren't getting fixed. And so then they were doing things to try to deal with this, like trying to figure out which person to assign the bug to. So it's a known problem in static analysis that you can have the fix rates can be low even though the false positive rate is low. So that's a known problem, but it's not emphasized in static analysis. So my point is that we should focus on that thing, the fix rate, more and optimize more for that. So I think that answers. I think what I've said is consistent with what Coverity said, even though the emphasis isn't the same.
Any further questions from the floor? Don't be frightened. Oh, I'm sorry, behind you, Brad.
Thank you very much. Hemsley Birkbeck. Can you say something about teams or parts of teams distributed geographically around the world and the effect of that? Because you put up a sort of a day and night working system.
Yeah.
And of course, the night moves around, the day moves around.
Well, let me put it like this. So the thing was negative, right? It said the nightly run, or it really means periodic. It doesn't matter when it is. The nightly, out of the workflow is the important part. But the nightly run was, say it was at night in San Francisco. Now, Facebook has the majority of the programmers are in San Francisco. So if the bug, if the fix rate is bad for running it at night for them, then that's just bad. So the geographic, for the argument that I made about the nightly run or periodic run, I would say, having a much worse fix rate than the live run with the code changes, that's independent of geography.
Okay, thank you. I was just intrigued by the remark about the French group and wondered about Indian software programmers and Chinese software programmers, etc.
No,
there aren't
so
nests like that.
Yeah, let me put it more clearly then. So the difference is time. So when the person makes a code change and then the code change goes to code review and the discussion is happening, maybe 30 minutes after the code change, then it's important for the program analysis tool to comment at that moment when the conversation is going on and when the people have paged in the discussion. That's the important thing, the paging in of the discussion. Now, if the comment was to come hours later, that would be too late. That would be out of the context of the discussion. And so the nightly run comes too late. If I was to do a run on the whole entire code base every 3 hours, it would also come too late.
So you're referring to also the cultural thing, that there's this programming language expertise group that's from France. There are many programmer and software engineering groups in India, and that you appear to have engaged in San Francisco, but with French teams of programmers. That's interesting because we actually do the same where I'm from. And not with outsourcing a bunch of the work to India, which has in the past been a question for large companies. So it's a practical thing about how large companies get software done. That might be an interesting thing. Oh, there's a question over here. So can we, there's a microphone coming your way.
You have suggested that improving the fixed rate is an interesting academic problem, and to me it sounds very fascinating, but the way you have described measuring the fixed rate requires to have a team of thousands of programmers. A lonely university postdoc can't replicate this environment. Would you be able to rephrase the problem in a purely mathematical way so that some small team can work on it?
Yeah, I can. Yeah, and so I don't mean to see one thing that could would be irritating for academics is when somebody like me goes into industry. Then I say, you've got to do things like industry, and that's not what I'm saying because you don't have the thousands of programmers. But what I am saying is that the problems we've seen impact upon the technical questions that you ask in academia. And so I would say this, don't ask a program analysis question where you will celebrate if the algorithm gives the answer in 5 hours on a million. You can find million-line code bases. Don't celebrate then. Celebrate if you can make an algorithm that on a large code base gives answers in 20 minutes on a code change. And so we could mathematize that question, but that's a better question for program analysis than the global program analysis questions. And so you see, that turns into a purely technical question. And I'm also saying, don't just go for algorithms with that characteristic. Look for the questions that the algorithm answers that can give the answer quickly on the code changes. Yes.
When you work on diffs, do you actually store the previous program analysis or something along those lines in the version control system so you don't have to redo it and can just work on the delta? So
yeah, what we do is we experiment. So he's talking about caching results from the program analysis. And we do that, but then sometimes we do experiments where we don't do that, and we say, see, this wonderful thing I showed you about that algorithm before, it can start from anywhere. So I could just start from the procedure and then see how far it takes me. And so whenever you're dealing with caching with large systems, it's very hard to predict beforehand whether caching or not caching will make a difference, positive or negative difference. And so we have found some cases where right now we're caching. We have found scenarios where not caching is the better thing to do. So the success of the method is not down to caching, but that can speed it up. And so see, this is a kind of question that you could ask as an academic as well, right? You could ask that